In this video, we're going to look at how to find and examine the local extrema for multivariate functions. So when we say local extrema, what we mean is max and min. That's at least what we call them in the Calc 1 world. So let's take a look at that first from a Calc 1 refresher. So in a first calculus course, we have a function f of x. So there's an output, right, of y equals f of x. Potentially has a local minimum or maximum y value for all x where f prime of x equals 0. So in other words, we're looking for the x values. So let's take a look at this function. We're looking for all the x values at which the rate of change is 0. So this is a graph of the function using Desmos, and one thing that we know about calculus is, and the reason we love derivatives so much is because it allows us to find x values where the rate of change is 0. So right there, if I were to draw the tangent line to that point, it would have, I don't know if I can draw it, a slope of 0. Okay, so that is how I can go about locating those points, is by setting the derivative equal to 0, solving for x. So let's go ahead and do that here as a refresher. So the first thing we do is we find the rate of change function, which is, in this case, 2x minus 5. So this guy, this output is the rate of change, and the rate of change depends on x. So the next thing I'm going to do is I'm going to say, well, when is the rate of change 0? For what x? So I'm going to say, let f prime of x be 0, and now I'm going to find the value of x for which that occurs. Okay, so I solve this equation, and I get x equals 5 halves, which is equal to 2.5. So that tells me that I have a critical point. We call this a critical point because it's only a candidate, right? Here it says potentially. This is a candidate for a local max or a local min, okay? And so the next thing I would need to do is we could do like a first derivative test where we could say, well, what are the slopes surrounding x equals 2.5? So for example, x equals 0 is over here, and so I can check that at f prime of 0, that the slope when x is equal to 0, well, that's 2 times 0 minus 5, is negative 5. Therefore, one thing that I do know is the function coming in to x equals 2.5 has a negative rate of change. And why do I only need to test one point? Well, the only way for a rate of change to go from negative to positive or positive to negative is for the rate of change to be 0 somewhere in between. That, or there's a discontinuity, but we're not going to consider that case here. So if there's an asymptote, then to the left and right of that asymptote, the behavior could be different. So I can pick another point over here to the right of x equals 2.5. Let's say what's the slope when x equals 3? And I can pick any value. I want to pick the easiest one I can. So I'm going to pick a whole number. And 2 times 3 is 6, minus 5 is positive 1. I don't really care about the value. I care about the sign. So I see that the rate of change is positive. That means the function is increasing. Therefore, at x equals 2.5, I have a local min. Great, so we have a local minimum there. Now that's in fact a global minimum because that's on a parabola, that's the smallest point is the vertex. And so I've located, in fact, the global minimum, but we always call it the local minimum until we have some way of verifying that it's the absolute minimum or the global minimum. Absolute and global mean the same thing. Okay, so that's the idea with Calc 1, is we locate these critical points. We can kind of check on the left and right of the critical point to see what the rate of change is, and how does this apply? And then there's the exception to the rule, of course. We have to be careful. Let's say we have f of x equals x cubed. Well, if we take the derivative, so the rate of change function is 3x squared, and we set that equal to 0, we solve for x, so we can do that in a number of ways, but the only way for 3 times some number to give me 0 is for that number to equal 0. If I do the divide by 3 and take the square root of both sides, I'll get x equals 0 as well. Okay, so I claim that that's a critical point, but I don't yet know how to qualify that critical point. Is it a local min or a local max, or potentially neither? Well, let's again draw this line, and so I'm pretending I kind of have a y-axis here. That's what I'm really doing. Is there's x equals 0. That's a critical point. I know the slope at x equals 0 is 0. So I can test a point over here, and I'll just test x equals negative 1. Well, if I test the slope when x is -1, I get 3 times quantity -1 squared, so that's -1 squared is 1, 3 times 1 is 3, so that means the rate of change is increasing. Or sorry, not the rate of change, but the value of y is increasing. So I might be tempted to say, this is a local maximum, but this is why it's important to check both sides. So at x equals 1, if I plug in 1 for x, 1 squared is 1, 3 times 1 is 3, and therefore the rate of change is also positive over here. Well, what gives? What's going on here? Well, if we actually take a look at the graph of y versus x, what we see is this function looks as a cubic, and it levels off just for a brief second, reaches a slope of 0 right there, but then takes back off again. So this is the exception to the rule, and therefore that's why it's important to do more than just plug in a point and see what happens. We've got to look at the rate of change on both sides of that critical point. All right, well now we're ready to move on to the Calc 3 extension. So the Calc 3 extension is very similar, except that a minimum or maximum value of z equals f of xy is achieved only when the rate of change is 0 at a point in both the x and y directions. In other words, when the rate of change in the x direction, the rate of change in the y direction, we call that the gradient vector. And when both of those components of the gradient vector are 0, that is when f sub x at the point, so a comma b represents one of our critical points that we found, when that equals 0, and simultaneously when the rate of change in the y direction at our point is also equal to 0. So, in other words, a critical point, xy equals, so x equals a, y equals b, is a candidate. I'm going to call it a candidate now for a local min or max, because it could be neither, if both derivatives in the x direction and in the y direction are equal to 0. Okay, so for example, let's take a look at a multivariate function. So in this case, we can clearly see there's a local max there. And as far as we can see, this appears to be a global max because it appears to be the biggest one within the window we're seeing. And then down here somewhere, I know it's off the screen, but we have a local, at least appears to be the global min, because according to the domain in the x and the y directions, those appear to be the minimum maximum values. So if we take a look at it, now we can look at a contour plot, and we can see that here are these contour rings that go from z equals 1 up to z equals 3, and we can see that that point at z equals 3 is the local max pertaining to that point. And then here we have another set of rings, contour rings, going from 1, 6 to 11. So we reach a z value of 11 here. I don't know what x and y value that are. We're not given that information, but that's our global max within the y domain and the x domain given. And then this point down here, sorry, again, that's off the chart, goes from -1 down to -3, so it decreases into the negative z territory, and that's what we appear to have as our global min. So when we think about the rate of change, there's a rate of change in the x direction. So I'm going to try to draw this parallel to the x-axis. So that's parallel to this axis here. And there's a rate of change of 0 going that way. But also, now parallel to the y-axis, there's also a rate of change of 0 going in that direction. So there are two tangent slopes. There's one in the x direction, one in the y direction. And of course, with directional derivatives, all of the other directions have a rate of change of 0 as well. So how do we begin differentiating, pun sort of intended, between whether we've located a global max or global min? Number one, how do we find these critical points? So here we have a multivariate function. Check to see whether the value is a minimum or maximum. So fortunately, here we have the graph of the surface, and it appears that at the point x equals 0, y equals 0, that appears to be a global, sorry, I'll draw this off the side, that appears to be a global minimum. Appears to be. So we're going to now mathematically verify this because, you know, our senses are deceiving sometimes. So what do we need to do? Well, we need to look at the gradient vector. We need to look at we don't have to look at it as a vector, but we need to check what the partial derivatives are. And I'm going to write that as a vector. So the partial derivative with respect to x, well, let's see. So the derivative of y squared, so that's, we're holding y constant. So this term and this term and this term are all 0. And the derivative with respect to x is 2x minus the derivative of 6x, which is minus 6. The derivative with respect to y, this is a constant, this is a constant, this is a constant. Those derivatives are all 0. Derivative of y squared with respect to y is 2y. Derivative of negative 4y with respect to y is negative 4. And I need to set that equal to 0. Now this forms what we call a system of equations. So if you ever encountered that, this is one of the reasons why that concept is important. So I'm going to solve the system simultaneously. So 2x minus 6 needs to equal 0, and 2y minus 4 need to equal 0 at the same time. Well, because both of these functions only depend on one variable, this one, if I solve, I get, let's see, I'll add 6 to both sides, divide by 2, I get x equals 3. Here, if I solve for y, I get y equals 4 over 2, which is 2. Therefore, I'm claiming I have a critical point at xy equals the point 3, 2. Now, I don't know what the z value is. I can check that by plugging it back into the original function, because that's what gives me z's based upon the x's and y's I plug in. So let's also examine, so we know that let's try to figure out whether that point 3, 2 represents a minimum or maximum. Well, right now, we don't know how to check, but we can look at a table of values near the point to help us understand it. So I'm going to pick, so there's my x value of 3. Whoops, there I am. There's x equals 3, there's y equals 2. And at x equals 3 and y equals 2, if I plug those points in, I get a z value of 0. And I take a look at all of the z values really close near that point. So I just chose 0.1 increments, so 3, 2.9, 2.8, and then 3, 3.1, 3.2, because I want to look at it in the neighborhood of my critical point. And then same thing, 1.9, 1.8, 2.1, 2.2. And I want to examine this. I want to look at the z values, and I see that this value of 0 is in this table the smallest value. So what I believe is because at 3, 2, the z value is 0, which is smaller than all of the z values surrounding that point that I picked in this table, it looks like xyz equals 3, 2, 0 is a local minimum. Well, that's great. So I have a table, I can verify that. And for the most part, maybe we can, as long as these functions behave well, we can kind of do a table test each time. Well, let's look at something a little bit more sophisticated, a little bit more complicated. Here I have x cubed minus 3x plus y cubed minus 3y. And I take a look at the graph and I see that it has all kinds of waves and shapes and curvature to it. So it's a cubic function in both the x and the y directions. So I've got an x cubed and a y cubed. Well, so let's again check the partial derivative. So we're going to find the partial with respect to x, because again, what we want to accomplish is the rate of change in both the x and y directions needs to be 0 in order for me to consider a point to be a critical point. The derivative with respect to x, derivative of the first term is 3x squared with respect to x, minus 3, y cubed and negative 3y are both constants. We're holding those constants, therefore those are both 0 derivatives. And then f sub y of xy, well, that's a 0 derivative, that's a 0 derivative. I get 3y squared minus 3. And I want both of those simultaneously to equal 0. So that means I need to solve the system, 3x squared minus 3 equals 0, and 3y squared minus 3 equals 0. There are a few ways I can do this. I can do this by substitution. I can solve one equation for one variable and then plug it in the other. I can do it graphically. Or I can use something like Wolfram Alpha to have it solve the system for me. To show that it's possible to do it algebraically, let's go ahead and do it algebraically here. So the first equation I'm going to solve for x first. So I have 3x squared equals 3, which means x squared equals 1, which means x equals plus or minus 1. Now what I need to do is do the same thing for the second equation, 3y squared minus 3 equals 0, well, equals 3. So y squared equals 1, which means y equals plus or minus 1. This is a little bit tricky at first, but I have 4 points here. I have x equals 1, y equals 1, x equals 1, y equals negative 1, and we'll look at that next.